Resume recording. Okay, since we have not met before, my name is Kung Nguyen. I'm the field application engineer at EDA Direct, and we are the authorized distributor for Mentor Graphics, which is now Siemens. Okay, so let me just move on here. So just a couple of marketing slides, right? Why do you need to work with us? We've been in the industry here for many, many years, since 1997, and we offer solutions for customer to do things like signal integrity. If you have FPGA designs and you want to visualize your circuit, after synthesis, you want to see the schematic, you want to trace two things, there are design visualization tools that we can provide. Some of these are beneficial for customer because they want to look at things like parasitics, they want to look at RTL, they want to look at gates through connectors and stuff like that. Okay. We also have solution in PCB layout and routing. What kind of layout tool do you use, Marianne?
We're using pads. Jeffrey Kuster is our EDA Direct representative that I talk to about any kind of technical issues I have.
Great. Yes, he is the other FAE that works with me, supporting the layout side of things. So that's great. Okay.
Yeah. So he's my buddy over there.
Awesome. Awesome. Nice guy. He can entertain you very well. Much more better than I can. Okay. So 1997, we signed, agreement and became Mentor worldwide distributor 2007, and here we are 2019, and that's the next circle. But anyway, we have agreement with Siemens, so now we not only selling Mentor products but also sell Siemens products. Okay. And because of all these years of engagement with customer, we are familiar with all these applications and the market space. Medical device, Intuitive Surgical is our customer, the big surgical machine. We have automotive electronics, and this is a short list of some of our customers. There's Neo, there's LiDAR from Velodyne, AI, and hopefully one of these days we'll put, your name on this. Again, it's just few companies. And then consumer electronics, medical device, automotive electronics, all kinds of stuff. These are our products and the vendors. So on the Mentor side, there are simulation capability for FPGAs, RTL simulation, Questa Model Sim. There are layout tools. Also Valor for design for manufacturing. Today we'll talk about hyperlinks, which is the SI tool. There are also thermal analysis at the chip level, at the board level, and at the box level from Mentor side. ClearSoft for ASIC chip design, concept engineering for visualization of the RTL designs and spice and gate level and things like that. And then on the Siemens side, we also support sell and support the mechanical tools. So there are SolidWorks users out there, but other users also use Solid Edge. And then for structural analysis, and at some point, many of our customers need to do structural analysis. And what do I mean by that? Whoa, wait a minute. I'm just designing a CPU board. Why do I need structural analysis? Well, because your CPU board is plugged into a chassis or some enclosure. And if it's in a car, it's subjected to vibration, earthquake, whatever, things might be falling off, stuff like that. Okay, so this kind of give a broad landscape of products from chip design to board design to system design. And then in some cases where customer might not have the budget or the resource to have the tool in-house, they will come to us for some service. And this is not design service. This is analysis service. So if you, let's say at some point, Marianne, where your design get too complicated or too many boards and big system, backplane and all that kind of stuff, and you don't want to run the analysis through all of these things, you can come to us and we'll so hopefully can provide some analysis service um, for you. Okay. So the agenda for today, we'll talk about the high-speed design issues, and then look at some layout consideration. Then we'll talk about DDRx technology. They have advanced so much that I can't even keep up in my slides, but at least we'll see the trend. We'll talk a little bit about power integrity analysis, or DDR. Now, power integrity is a subject on its own. This is about designing the power plane, about filtering, all those planes that you have. And because of the DDR memory subsystem, it switches really fast and consumes a lot of current, and the power plane needs to be clean. There are effects from the SI world into the PI world and vice versa. So we can look at some of those effects just so that people will be aware that when you're looking at a signal and it looks bad, it's not always an SI issue. It can be a PI issue. If your power delivery is not clean, your plane is, fragmented so much, you got crosstalk, EMI, it can affect your SI world. Okay, so and also for DDR analysis, nowadays vendor provide the IBIS models that have power aware capability. And what this means is that in the past, when they give you these IBIS models, they will assume that the power delivery is clean, and they just measure the timing arcs, for those signals. But nowadays, due to dense board and a lot of switching, they characterize the behavior of the memory chip with power fluctuations, and they call this power aware IBIS model. We support that, and customers should simulate with that in mind. So it is short of saying doing power integrity simulations without doing power simulation, power integrity simulation, just turning it on. Because if you do a PI analysis, it'll be a little bit more elaborate. Okay. And then SI-PI co-simulation, as I mentioned before, looking at the effects from DDR switching into the power plane. And then we'll mention a little bit about how we can incorporate the 3D full wave solver to create a hybrid 2.5D and 3D simulation. Now, this is a very big subject in itself, and I hope to diffuse a lot of the confusion and at least make people aware of the importance of having the 3D full wave solver. The need for this is for cases like if you have DDR4, you're running 2400 mega transfer per second, very high speed. The effects of the traces, the way you route things, the way you do back drilling, your via structure, do you have non-functional paths or not, the sizes, the separation, all these have effects at high frequency. And when I say high frequency, I don't necessarily mean the megahertz. I mean the slew rate, right? The switching time between 0 and 1. That gets shorter and shorter and shorter. And that's what we call high speed. You can have a slow clock, but very fast edge rate. Okay, you can have a 10 megahertz clock with a very fast rate, and that will be considered a high-speed design. So for that kind of analysis, you will need the full 3D field solver, and this is not meant for everyone, but you need to take that into account. And at least my objective is to make people aware of these benefits. And then we'll follow with some demos. And I can do demos all days, and there's not enough time to do, every single demos. But hopefully, I will highlight enough areas to stir interest, and hopefully that you can relate from what I'm showing in the demo to your design. and we should have a separate discussion. Contact us. I'll be more than happy to come by, take a look at your design and discuss your requirement and blah blah blah, and we'll do what's right for each customer. Okay, so that's really the agenda. How do you position the simulation in the design flow? This is just basically showing a typical design flow where you will design your schematic, which involve part selection, packages, connectors, stack up and blah, blah, blah. You will push it through layout, and that's where you try to route everything, and then you get the prototype phase, and that's where you power up the board, and that's when you first do the functional testing and debugging and making sure your DDR is working, your clock signal looks good, and all that good stuff. And if everything's okay, you send that system out for EMI testing and more debugging, and you may have to loop around this a few times. So that's the normal design flow. What we are proposing is that you should position the simulation throughout the whole process, the whole phases, the whole, even in the beginning. So how does that help me? Well, if you are thinking of designing your next board, you don't know what stackup would be best for you. Okay, so there's some experiment on that. What you don't want to do is pick something, or somebody gave you, here's the stackup, just use it, and then may have to struggle at the end. That's not the optimum stackup, make changes. So in the beginning, you can actually go through different type of stackup scenario. And if you have things like flex rigid in your design, it will be crucial to simulate. Hey, my board is going through the flex, and the flex is 2 inches. What does that look like? Now, obviously, in the early stage of the game, the simulation will not be accurate because you haven't got everything done yet. But at least you will be able to see, oh my God, this signal after 2 inches, it looks really bad. I really need to focus on this, and then for part selection, maybe if you have an FPGA design in your product, which package should I use? Should I use BGA? How many pins? How do I assign my pin out? Things like that. What if I don't like Micron memory chip? What if I like SK Hynix or Samsung or whoever else? What if I use by 8 or by 16 or by 32? What if I do this? What if I do that? You will be able to simulate those type of scenario, which will drive your schematic. Okay. Oh, now I selected that package for the FPGA. So now let's do the symbol for the schematic, and then that package and the simulation result will drive the constraint for the layout. Oh, these signal has to be on this layer. The trace width has to be, so and so, and 4 vias, 2 vias, blah blah blah. So this will help drive the schematic and the layout. And then before you fab the board, you should do a simulation again, and that's what we call post layout simulation. This is the last time, the last chance for you to catch any mistake. So on your DDR subsystem, right? Your argument might be, oh, I just copy the reference design from Xilinx, development board. I just copy every single pin. I use exactly the same value, same length. It should work. Well, no. Um, that's that board with that stack up. This is your board with a different stack up, and different routing. That's give you that last chance to find any potential issue, because once you get to the prototype phase and power up the board, it will be very hard to start probing these kind of signals. Now, I don't know about you, but in the old days, things were spaced out. I can bring signals out to test points, to mixer, connector, connect up to the logic analyzer, blah, blah, blah. But nowadays, you can't do that. There's no such thing as a prototype board. Your prototype board is your final production board. And you can't, I don't know, people still doing this, but, plan 3 turns for the board spin. Oh, don't worry about it. First board is always prototype. No, if you get it right, that's it, right? So there's cost involved in spinning the board also. Sometimes people may not have that choice, but at least if you embrace this flow, hopefully we will be able to fine tune and catch issues along the way so that by the time when you actually fab the board and bring up in the system, a lot of things will be caught beforehand. Okay, so that's really the how we recommend customer to position the simulation in the design flow, which is throughout the whole design process, not just at the end, right? Um, things been done. You can't change, right? If you have the wrong termination on your clock net, you put in a parallel termination, and the best way would be series termination. How are you going to do that? You're going to fly the pin? You're going to cut the trace or what, right? So that's the idea behind this. Okay. Um, and then what are some of the PCB design issues that you might run into? So for the general interface, you have timing, which is, do I have enough setup and hold time? Does my signal arrive early enough or stay around long enough? Do I have crosstalk? Just because I reroute the board from 12 layer to 8 layers and everything fit and everything routed, that means it's going to work, right? No, because when you're packing signal closer, there's more chance for crosstalk to appear. And in today's PCBs, you have a lot of power planes to deal with. You have 3.3, 2.5, 1.8, 1.5, 1.2, 1.1, 1.0, 0.9, blah, 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 and all different multiple versions of this. And you cannot have a full plane on your stackup. So you end up cutting, right? One layer will share 2 or 3 rails. And because of these, you have openings between the plane and you have signal running on the top and on the bottom. And when signal run through a split plane like that, there are potential problems. The signal will radiate the electromagnetic wave and it will couple to intermittent to in adjacent layers. Okay, so crosstalk and that in turn degrade your signal quality. Your square wave doesn't look like a square anymore. It looks something weird, right? So how do you deal with that? So these are the issues. And then for the DDR subsystem, DDR 2, 3, 4, the main objective would be, hey, I'm targeting 400 megahertz, 800 megahertz, 1600 megahertz. Will I be able to run it at that rate? Okay, do I need to deal with a slew rate derating? This is mucking around with the switching, the ETH rate for the controller and the chip. Do I need to do right leveling? Okay, and if you have SerDes, PCIe Gen 1, 2, 3, 4, 5, if you have USB 3.1, you want to look at things like loss. Okay, my signal is greatly attenuated. Do I have any impedance discontinuity because I have boards and connectors and backplanes and lots of vias, right? When signal go through vias and the connectors from the backplane, the impedance changes, okay? And then do I have, bit error rate? How bad is my bit error rate? So these are the things that you can have as PCB design issues on the SI side. On the PI side, do I have enough metal? Is my power plane big enough to accommodate all the current and minimize the voltage drop from the regulator to my device? And then for decoupling, do I have enough capacitors? Are they in the right value? Did I mount them correctly? Should I have via in the path? Should I run one trace down to the plane or 2 traces? Things like that. So they're equally important is on the power integrity side. People normally don't think of it that way. People think that, oh, I have a power plane and it's all copper. No, it's not. Because at the end of the day, you have all these via, you have these holes, you're poking through these planes and you create narrow channels. where current may have to go through, um, and there may not be enough copper to deliver the current, which create more high impedance and higher voltage drop. So things like that. That's on the PI side. Hopefully, if you've done your SI side, no overshoot, crosstalk, ringing, all that thing, and you've done your power integrity side, big plane, no, not much ripple, then your EMI test will be better. What you don't want to do is let's just run things through and then let's build a system and go to the lab up in the mountain. Let's run some FCC tests and oops, we got some, spikes, some harmonics, and let's pull out those capacitors, let's pull out those aluminum foil, copper, whatever, and then try to fix those at that time, right? Those are patching, those are not fixing, and it's kind of late. So these things will lead into the EMI. And I can guarantee you, I don't care if your product's working. If it does not pass FCC, Class A, Class B, it ain't going out the door. You need to pass certification. Um, okay. So things that can affect the signal, SIPI and EMI is your stackup, okay? Because in your stackup, you can control the material, you can control the thickness, that can affect the impedance. FR4 has different loss than Roger, than different types. So you can vary your stackup to meet certain impedance. And there are many ways to meet your impedance, and not just changing the trace structure. You can vary your stackup. And also, depending on the material you use, you may have more loss than necessary, right? And then crosstalk, how close are you spaced these layers? Do you have uh, power, signal, power, or do you have power, signal, 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 power, or how do you do your stackup? Because all of these have effects on crosstalk and impedance. So the stackup is very important. And sometimes this is not taken, seriously enough, in my view, because I've heard from customers saying, well, our fab house determined the stackup. They gave us this stackup, and that's what we work with. And we're kind of stuck with that stackup. And that's true. Don't get me wrong. The reason they give you that stackup is because it's something that they can make. They don't want to go through difficult stackup, 1 mil, 2 mil, mixing all kind of different materials, and they can't have a high yield, right? But you, on the other hand, uh, you know, keeping cost in mind, but you also want performance. And for performance, you might have to modify the stack up, the thickness, the material to meet your signaling requirement. So where's the solution? Is somewhere in the middle. And how do you determine that? Through simulation. What you don't want to do is go through the whole process and find issues on the bench and then having to change the stack up. That's bad. For PI, you want to make sure there's enough copper, thick plane to minimize the voltage drop delivery. You need the plane need to be closely spaced uh, to filter any ripples for you. So if you have power, signal, power, that's better than power, signal, 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 power. Um, and then you end up with adding a lot more capacitor. So, and then do you need to add stitching vias? Because, for example, DDR, sometimes they, for doing refresh, they use a lot of current in amps. Do I need to add additional stitching vias to relieve the current choke points? Okay. And then EMI, you can't really fix EMI issue, but you can contain, you can mitigate by having large enough planes to shield these electromagnetic waves from escaping. Um, but sometimes you can't do that because I have to have 3 power rails on one layer, so I can't have a big plane. And sometimes these things will escape from the side. If you're running some high-speed signal near the edge of the board, you can get into a case where the radiation will, escape from the side. So a lot of these things you need to worry about. Okay. So what are some of the layout recommendation? I call this consideration. I don't necessarily call this a guideline, because what guideline means is a lot of people just follow it blindly. Oh, Xilinx said this, Intel said that. I just have to follow, and they don't understand why. But these are considerations to think about it. Sometimes you may have to do this kind of things. Um, but if you do, know that you are playing things dangerously. So, for example, in layout, you try to avoid signal crossing the split plane. So here's a little graphic that show I have a signal that crosses through the split, okay? And the way the current flow, I don't know if you remember, the right hand rule. If current flow this way, the magnetic field is going to go around it. And if it doesn't have a plane to shield, it will escape through the openings, and it will couple. So current create magnetic wave, magnetic will create current on other layers, and that's what we call loosely crosstalk. I actually have seen people routing clocks, not just crossing like this, but going along the way like this, and that's really bad. Okay, so try not to do this, and if you do, you need to cross very quickly, minimize the gap. Instead of doing 45 here, you might want to do straight. Things like that. Okay. Using match impedances, we all know that, but we probably don't know why. The reason is we want to minimize the inter-symbol interference, the charge from accumulating from one bit to the next. And we want the energy to transfer from the transmitter to the receiver completely without any reflection. And that can be achieved with a matched impedance. Crosstalk, right? We want to isolate the sensitive bits, the data strobes, the clocks, even the reset signal. Some people think, oh, reset only happened in the beginning and it's static. Well, it is important because if you have a reset line next to a data line which switches a lot, the switching activity can cause noise into the reset signal and may cause sporadic system resets. Okay, so and the best way to mitigate crosstalk is space them further apart. Okay, and there are things about power supply. Use precision register, short and wide traces. I'm not going to go through everything here, but there are some recommendation in here. And then for DDR, you need to understand the ODT, and which can be different if you're doing a write and it's a read. Okay, so how do you determine the trace impedance? Let's say on a data line, let's say your driver is driving a 30 ohm output impedance, and your receiver, your micron or whatever, is receiving at 48 ohm. So how do you determine the impedance of the trace in the middle for the write? And then on the read, the numbers are different. Don't just go by 50 ohm, right? That's just an old rule. It isn't wrong. So play around with the ODT, simulate it, and see which one you should use and what will drive your trace impedance. One thing I do want to mention is in terms of power consumption and signal swing. Sometimes when and I've seen this in the real customer design where they were showing an address line and it was working fine, but it was ringing, and it wasn't overshooting. It wasn't, and the amplitude was not dangerous. It wasn't anywhere close to the threshold switching, but it was ringing. And this was a battery operated product. And these ringing are consuming dynamic power. Oh, come on, that's just one address line. That's microwatts. Well, yeah, but you have 10 of these, and you have a lot of signals that are ringing like this. They will add up. And not only they consume more dynamic power, they will also radiate more EMI. Those ringing have very high frequency components in them. Okay, so you may even have to lower, terminate it better, or lower the switching range to save power. Okay, so things like that you can do in the interest of saving power consumption. Okay? So in terms of the tools, what can we do? And what I like to call this is the baseline analysis. Baseline analysis is something that you should do on every single board. What that means is you should be able to run simulation in pre-layout. That means my board's not done yet. I'm still going to stack up. I'm experimenting with the length, with the termination resistor, with the VS structure. Let's run some simulation, see what the things look like. Okay. I don't want to put in both termination scheme for my clock, both series and parallel, and then on the bench I'll figure out what it is. No, let's just do it now and be done with it. Okay. So the things you can do is look at termination. Okay. You can look at the EMI. Yes, you can look at EMI. If you have a chip that is switching very fast, you can simulate that signal on the top layer for 5 inches and see the effects of the harmonics and the radiation. And you can compare this to FCC Class A, Class B, or whatever limit you want. At least that gives you an ability to have some visibility into this kind of problem. I'll share another example from a real customer, medical device, and what they used was a relay, and in the beginning it has to switch 400 volts in some milliseconds, and the relay will open and close and switch, and at that time you have a very fast edge, and that one created EMI issue. And they had to end up doing some shielding on the top and on the bottom. So even things like that can be an EMI issue that can be simulated. Okay. And then the beauty with simulation is you can probe anywhere you want non-destructively. You're not affecting the circuit and the test. You can probe underneath the ball, the traces, the via in the middle. You can't do this on a real board in real life. And even when you can access the signal, you will load down the signal. You will affect the behavior of the signal by touching it. In simulation, we're not touching. There's no effect, zero effect on the signal when we're probing. Stackup editor, this is where you would play around with your stackup and make sure it's okay, optimum from a cost standpoint as well as from a performance standpoint. And we can simulate things like trapezoidal shapes, right, or surface roughness. You can simulate all that thing in both pre and post layout. And then the ability to do sweep analysis. So if I have a clock trace and I don't know how far can I drive the clock. Is it 2 inch, 3 inch, 10 inch, 20 inch? So I'm going to do a sweep, and I will sweep the length and see at what point my signal looks bad. I can sweep the width. I can sweep the thickness of my dielectric. Should it always be 10 mil, 5 mil, 3 mil, 4 mil, or what? Should I sweep the dielectric constant, FR4, from 4.0 to 4.1, 4.2, 4.3, 4.4? Can I sweep the resistor? Can I sweep the voltage? So that sweeping capability will give you more visibility into how your circuit will behave, and you can design for worst case and best case that way. Okay, I'm going to skip through some of this. I'm not talking about all. And then if in your design you have a multi-board setup, right? A motherboard, daughter board, connector. In this case, it's showing a DRAM DIMM, but it doesn't have to be this. It can be a backplane. It can be a excuse me, a transmitter board, receiver board, multiple slots. Whatever. We will be able to simulate across all of these boards. Eye diagram. Yes. This is the standard for analyzing things these days. Let me just bring something. So in one eye diagram, you'll be able to see overshoot, undershoot, jitter, things like that. And all the SerDes channel must use eye diagram, even DDR4. Okay, so those are what we call the basic baseline analysis. For DDR, the tool has the ability to help you walk you through. Why is it switching here? Okay, walk you through the setup and be able to analyze the whole memory subsystem with minimal setup. We'll go through some demo and you can see how that works. But we'll generate a report on the whole memory interface with every signal that you have here. So in post layout, that'll be everything. In pre layout, it'll be whatever you simulate. And if there's any failure, we can click on the failure point and the waveform will come up and show you how we measure this. Okay. And with DDR, you need to be concerned with the VIA models, how you design your VIAs. Uh, I don't know, but is using through holes good enough? Should I use buried, blind? On lower speed, through holes may be okay with the VIA stuff, but on higher speed may not be okay. So the process of setting up this simulation for DDR analysis takes somewhere about 5, 10 minutes, 15 minutes, depending on the complexity, and the run takes about minutes to an hour, depending on how many signals you analyze. But the benefits for you is that you have a complete analysis of every single signal that you want on all the reads and all the writes, on the address lines and all the data lines and control lines. Um, that really beats debugging on the bench, because on the bench, how many signals can you monitor? And as soon as you probe something, you're affecting the results, right? So there is a wizard in the tool that walk you through. I'll go through a demo on that. Okay, some differences between DDR3 and 4. 3 is 1.5 volt, 4 is 1.2. So there's power saving, there's higher bandwidth. Um, VREF is fixed, right? The reference voltage is fixed for DDR3, which is 1.5 volt divided by 2, or 0.75. So that's the switching point. But for DDR4, it's programmable. It's not always half of the supply. Okay, and the I/O standard for DDR4 is pseudo open drain, not SSPL 1.5. So there is power saving when the value is a 1, right? When you're driving a high, is open drain, so there's no current flowing in a high state. Whereas in DDR3, whether you're in a high state or low state, you will consume current. So that's some differences between the two, not just the speed. Okay, and then for the low power case, there is more speed because of high frequency and lower voltage compared to DDR3, and there's power reduction and I/O standard, there's LVSTL, low voltage swing terminated logic, and so there's some of these differences. How would I create a pre-layout simulation? And this circuit, I will run the demo. But here it's in the slide. So I can just model, there's the clock signal, there's some address line with some pull-up that I want to do. There's some mask signal, there's this DQS, and there are 4 DQ lines with different lengths, different via structure. And so I want to create this quickly, and this is based on some stackup, and walk through the wizard and see the result. So this is what it would look like for a pre-layout simulation case. Okay, and if you're using pads, or if you're using DX Designer, that's Mental Graphics schematic capture, we can go directly from schematic into simulation without drawing these kind of things. Okay. So in case you are trying to route DDR, here are some of the areas of concern or point that you need to worry about. Is you need to, it will be constraint driven routing, right? And hopefully those constraints come from simulation. How long the trace can be, what are the spacing, okay, what are the structures. So those are constraints. And there are things that you need to observe while you're routing DDR. There's width clearance rules, layer restriction, path entry rule, differential pair rules. So a lot of these things, and Mentor also offer a slightly different path product. It's called Path Professional. where you can sketch these routes uh, and allow you to route a lot quicker with constraints. Okay, and you can route, reroute, modify changes very easily. This is not auto route. This is constraint auto route, but follow the scheme that you want. Okay. So here's another more detailed video that shows the FPGA up here, which is a DDR controller, and there are address bus that are going down here, and data line that goes through all these chips. So how would you complete the route of this DDR3 subsystem? And I would say maybe a few days to get an optimized route, maybe a day, maybe a few days, depending on your experience. But you may have to reroute, and over. But here is how it works in if you're using Path Professional. And again, this is not about tool layout tool, but I do need to mention it in that here you will sketch the way this should be routed. The tool will route it to that way, and then you can select a different section, and you say just go across. Tool will do that for you, and then switching layers and complete all the remaining unroute net and just go across. Then it will finish for you. So that's the address line, and then for the data line, you say I want to route this way. Oops, I really didn't want to do that. Let me redo that. You just sketch a very tighter way, and it will route for you. Here's a case where the signals are crossing, right? And you need to put in a via structure to break this into a more straight trace. And you can change routes and reroute all this very quickly. Obviously, all this can be done with the manual. But why is this important and why am I showing you? Because it's related. You can't just simulate on the pre-layout and then wait for the board, wait 2 weeks, 3 weeks for the board to be done. With this, you can have a closure a lot quicker, and how things are routed for the DDR affects the simulation. And with the constraint routing and spacing rule, we'll have a tighter control on the results. Okay, that's why I'm showing this. So next thing to look at is the ODT-I shifting effects in DDR. So the test case would be I have one driver, my transmission line is 50 ohm, and I'm driving a micron chip, and I want to vary the ODT to see what the I look like, and I'm running this at 2400 megabit per second data rate. So with DDR3, when you sweep the ODT, for example, from 40 ohm to 60 ohm to 120 ohm, the center of the I stay the same, and that center is 0.75 volt, which is 1.5 volt divided by 2. And with a smaller ODT, your I height will be smaller, and the bigger ODT, will be bigger, but everything's centered at the same point. The I just get bigger or smaller depending on ODT. However, if you're running with DDR4 and you're changing ODTs, it shifts down. So 40 ohm will have the yellow I, and then the orange or brown, I don't know how you're seeing it here, it's 60, it's a shift down, and the ODT 80 is shift down. And to make it more complicated, you can have different ODTs and different references for each of the data bits in DDR4, which make it really complicated, because not all the data lines are the same. Some will be shift up, shift down, and they're all perfect. They're all good because of the setting. So it's really, puzzling, complicated to go through all of that on the bench. Okay, but here's simulation. You can do a lot quicker. And then if you're using LP low power DDR4, the I now shifts up depending on ODT. So if you think about it, all these bits shifting up and down, it's really hard to debug on the bench. Okay. All right. So move on. Power integrity pre-layout. What this means is I need to decide how big my plane cutout should be, and how much decoupling capacitor I should use. So I need to do a pre-layout simulation to make sure the shape's correct, the number of capacitor, look at the impedance, the curve, blah blah blah. Right. So that's pre-layout. And then in post layout, once the board is done and routed with all the switch keys, holes and vias thing, let me do that again. Can I detect any current choking point? Is my impedance consistent? Right. The two slides are about power integrity simulation. Okay. But what we're more interested here and have time for is the power integrity effects. What that means is if I am modeling a DDR subsystem where I have 8 data lines switching some PRBS, right, so the random bit sequence at 2400 mega transfer per second, and if my clock is running at 1.2 gigahertz, and I'm probing on the DDR power pin, okay, while these guys are switching, what does the power pin look like when these guys are switching? And the simulation will show that you have about 150 millivolt of ripples of noise, strictly due to the switching behavior. Okay. Now, if you do this way, then you can at least isolate that this ripple come from DDR. If you don't do this, and if you go to the bench and you measure the power supply voltage on the bench, you will see all kinds of ripple, and you don't know who's doing what, right, where it's coming from. But here we can actually isolate, and based on whether or not this 150 millivolt is acceptable to you or not, you can now fix a coupling capacitor or filter so that when your DDR is switching, it's not pulling down, it's not creating issue on the plane that may be shared with other devices. Okay, that's what we call looking at power integrity effects. Now, how do we do co-simulation? So in this simple example, and again, this is showing in pre-layout, but you can do this in post-layout too. So in this simple example, we're saying that there's some vertex chip driving a signal through a via, a through-hole via, going from top to bottom, and the receivers on the bottom side. And we have some plane structure here, and this is our stackup. So when the signal goes through the via, what are the effects on the power plane, or the power plane having the effects on the signal, right? So here's a quick video showing that if I run a simulation without taking into account the power integrity, this is my signal. That's what it looks like, the yellow one. If I enable plane noise, okay, how is that going to affect my signal? So in the beginning, they're okay, but as these guys propagate and ripples around, the plot actually deviates. So around this area here, right? So this might seem little for you, but this is just a single instance to show you the effects of SI and PI co-simulation. Now you need to be aware that doing this is doing both at the same time. So it will be, compute intensive. So you want to pick out a few and do a few, not the whole thing, have the whole DDR switching and look at the whole power plane. You can do that, but it will take a lot longer time. So this here just to show you that there are effects from SI, from doing SI-PI co-simulation. Okay. Let's introduce some 3D field solver for you. So the point here is if you have some connection from one device, let's say on the left, going to some other device on the right, so you want to be able to look at the signaling here very accurately. So the desire would be to run things in full 3D field solver. But if you do that, the time penalty is huge. It could be in hours and days, okay? And you don't have that time. So what we've come up with is we've come up with this hybrid solution where we say, for the middle part, where the traces are basically simple, just going left and right, we can solve that using 2.5D. But for the structures around the pin, that's where the via is, that's where the pad, the connector, back drilling, we may have to do those in 3D, and then we'll combine them together and bring you from hours into minutes of simulation, and memory requirement from 50 gig to 5 gig, right? And for that, you can look at insertion loss, return loss, near end crosstalk, far end crosstalk, and be able to converge on the result a lot quicker than modeling everything in 3D. Okay, that's really our solution. It's a hybrid case. So what are the steps involved in doing this? You will open your board, okay? You will look at the net, okay? And then you will select the net, a bunch of data lines, address line here, okay? And that defines this location on the board. So this is between the controller and the memory chip. So these nets reside in this region, okay? And what we are saying here is go ahead and cut out this region and create a 3D area for that. And what it does is it will cut through all these signals and create a multi-port S parameter model for this. If you're familiar with S parameter model, then that makes a lot of sense here. Once we create those ports, we can set up the solver, uh, and solve for that region. And at the end, what happened here is it now cut out that section of that board, right, from your main board, that little section, and sends that into a 3D viewing environment where you can look at the via structure, the fins, doing your back drilling, whatever you want to model in here, and define some conditions, right, starting, ending frequency, meshing, grading, and all that thing. And the tool will solve for both S, Y, and Z parameters, okay? And at the end, you will get one module that you can stick right into your schematic. This is a simulation schematic. You can attach the vendor drivers and receiver, right? It might be an IMX, might be Xilinx, Cavium, whatever. You attach on the other side the memory chip model. And now when you run the wizard, it is taking advantage of two automation for you. One is the automation of running the full DDR analysis, okay, which save you a lot of time and do a complete analysis. Number two, we are using a solved area of the real board, which was solved in 3D using the full 3D view solver. So any analysis through that section will be a lot more accurate than not doing it. Now, this is not for everybody. If you're running DDR3, 400 megahertz, you probably don't need to do this. But if you're running DDR4 at 2400 rate and above, strongly advisable to do this kind of thing. Okay, so we're taking advantage of two automation at once. And for demo purposes, I use things like the Xilinx VCU 108 ultra scale development board, and I pick and poke, all kinds of things on this board to show customer demos. Similarly, if you're doing Altera, in this case, it's showing, let's go back. For Xilinx, it has two banks of DDR4, one on the top, right, and one on the bottom, and they actually use ECC. This board also has PCIe Gen 3, 8 gigahertz, HDMI, all that kind of thing, SD card, USB, blah, blah, blah. And on the Altera board, same thing, PCIe Gen 3, Ethernet, gigabit, and then DDR4 is now a module. So instead of having the memory chip on the board, they're going through this socket, which is a non-standard socket. And they plug this daughter board in, and now they can access DDR4. Or they can have, an IO board or whatever, right? So this was the implementation. So I use both boards equally to run simulation. But for the demo today, I'll focus more on this board. This is a very simple board. BeagleBone, a lot of people use this in real life to design projects. What's nice about this is it is a full ARM processor. There's a DDR3 interface, one chip, very simple, 512 meg. There's NAND flash, there's Ethernet, there's USB, there's HDMI, there's SD card slot. You have the whole schematic, bombs, and everything. and this is available in path format. You can actually go to path.com and download the design file for free, all that stuff. And maybe you have to copy things, reuse a symbol, look at the layout, I don't know, whatever. So we provide this for customer, and you can base your next design on this or something like that. Okay, so that's what I use. A little bit of talk on the rigid flex. So we are seeing more and more of this stuff in the system. Now, this may not be directly involved in a DDR subsystem. I just want to mention it in the sense that, your system might have rigid flex, and you should and will be able to take advantage of simulating with it. And it's not easy to analyze through the rigid flex, but we make the process a lot simple for you to go through. And this will short answers we can do rigid flex. Okay. All right. So the idea here is not only we worry about DDR or SI or PI, but there are also thermal involved. Board might heat up. That will change the electrical characteristics, and you may have to go through, loop this a few times. And if you have an integrated environment, don't have to import, export stuff from different tools and deal with all these translation issues. So just stay in one. Okay, that's really the case. And that's our contacts. So for now, let me just turn this off. Don't want to do email while I'm working here. So let's just run the tool. So quickly, I'll show you that we'll run the BeagleBone first. Okay, that's simple. This is a post layout. So first you read the board in, very quickly. And here's what it looks like. So the first thing to do always before running any simulation is to look at the stackup. Make sure that this is defined correctly. If it's not, then all bets are off. Right? Is the thickness correct? The dielectric value correct? Is there solder mass or no solder mass? Right? Thickness is okay. In here, we can actually model things like trapezoidal shapes. So this is due to etching effects, right? So the first simulation, you probably don't want to enable trapezoidal trace shape. You want to set things up, want to go through, see timing, blah, blah. When you think you're done, then you go back and you enable this stuff, and then you simulate to how they're made. And also you can enable the surface roughness, right? These are the glass weaving effects on the PCB that you should turn off in the beginning to get things going. But before you release to production, you should at least run some simulation with both of these turned on. Okay, and then there are other things in here, dielectric loss tangent number, blah, 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 in here. And it's pretty easy if you need to make some changes. For example, if I want to change this 36 mil to something smaller, fine, I'll make it 5 mil. If I want to add a layer to this, insert above, below, a solid plane, no problem. Oops, that's in the wrong location. I want to move it around, move it down here, no problem. So very easy to model this. Okay, this is what we call stackup editor. So let me cancel this before I screw things up. And one thing to remember here is you need to understand what yes mean and what no mean. Right? So sometimes yes is a good thing, sometimes no is a good thing. So in this case, all changes will be lost. Do you want to exit? Yes. Okay. So that's the thing. Now we need to run the wizard. So we run the batch simulation, and the wizard will come up, and we support DDR, DDR2, 3, 4, low power 2, 3, 4. We also support NV, non-volatile DDR2, NV DDR3. And if more memory structure comes about, we'll support those. So next, so in order to save some setup time, I'm going to import a setup file already, okay? And it might show some warning, right, because of the IBIS file, not quite set up correctly, blah, blah, blah. But you look to this, in this case, it's okay. So what we're doing here is we're setting this up for DDR3. You can also change it to different, memory subsystem if you want. We are running this at 1.5, but you might want to run at 135, 125. And then the data rate, whatever you want here. So right now it's set up for this case. Next, what we're saying here is U5 on the board is the memory controller, okay? And then it only has one memory chip, which is U2. So there's ability to model different slots and DIMMs and single-sided, double-sided, blah, blah, blah. But in this case, it's just one chip. And here are the IBIS model for the controller and the IBIS model for the memory chip, okay? So just specify it here. Next, what are we doing? We're going to do a write cycle only. We can do both read and write. We can look at clock to strobe, so that's clock to DQS. We can look at address command timing, different threshold, blah, blah, blah. Now, if you don't understand some of these things and you need help, just click on help. And it opens up over here on the different windows. But here is where it's loading. And it will tell you what the options are, okay? So help is along the way. Next, we are looking at these signals, right? RAS, CAS, address line, bank, DQs and stuff like that. Again, this is already a setup file, so we don't have to go through, specify each one of this. It's just showing you what was selected. So DQS0, DQS1, the mask, tying to the byte lane, right? And then the clock that being used, right? So DDRC, okay. You may have multiple clocks. These are the address line, A0 to A14, bank address, RAS, CAS, write enable, okay. CKE, chip select, ODT controls. And what are we analyzing? We're analyzing everything. All the address lines, all the data lines, all the control lines. If you don't want to analyze something, just uncheck it, okay? Next, this is the most important thing, is to look at the ODT settings. So for the ODT setting, you can have selection depending on the controller that you have. So you can try something else. And same thing for memory. Micron, you can pick your ODT settings, okay? Different type of ODT setting. So that's for the DQS, for the DQ, and the DMs, okay? And just go through some of this. And then here, there are more options for you to deal with flyby topology. We can run it multiple times to characterize the channels, and on one time you specify the condition, fast, typical, or slow. If you want to specifically have some right leveling value, we will extract this for you from the layout too. But if you can save an existing file from before and bring it in, whatever. These are configuration for right leveling. And then these are what we call the timing models. Timing model mean we will look at things like TCKAC, so clock to address and command. This is basically coming from the data sheet, but it is different for each controller. Each controller will have different type of requirement. What is my minimum setup time? What is my minimum hold time? For IMX is different, for dialing different, for Altera is different. What we have here is a generic default number. What you will need to do is you will need to edit this to your controller timing to have more accurate checks. But the first run, you can use the default timing model to see where things are, okay? So that's what we'll do. So this is TCKAC, TDQS, all this stuff, right? And now oh my God, this looks really complicated. Well, it is complicated. This is a memory subsystem. This is not, it's very complicated timing, but we make it simple for you, okay? So that's the controller timing, and here's the memory chip timing. It has different type of requirement, different hold time, different setup, different margin, different ranges. So that is why we provide a default model for you to use at first. Okay, next, what is this? Round trip delay. And again, it depends on what you choose. If it's DDR3, then you see a bunch of things. If it's DDR4, it's something else. Next, these are just the pattern that we will use to drive into the interface. So we will use 8-bit PRBS. We will drive randomly these patterns into the A0, A1, or the address line and data line. So if you don't like these patterns, you can put your own, but why would you want to muck around with that? So let us do that. And then you can also include the crosstalk effects. What this means is on a post layout board, we will look at signals that are adjacent to these memory signals, and we will incorporate those effects in the simulation and tell you if you turn crosstalk off, then you are passing with these values. If you turn crosstalk on, then your results are derated by so and so and so. Now, how do you specify some of those effects? So, for example, you can go into coupling threshold. You say enable this and coupling threshold, and you can specify, the spacing requirement or the millivolt of coupling. Or if you want to get more complicated, you can go in further and say, you know what, my memory subsystem signals are on this layer. I have some partial plane. It has some opening. There's some different layer. I want the tool to go in and figure out whenever it sees some structure like this with some spacing, with some distances, that to take that into account and be able to incorporate crosstalk effects between these vertical layers for me, not just horizontal, okay? And you can specify, the distance and stuff like that. So this is a little bit more detail, but once you specify some of these constraints, we will go through and look at your exact layout and find the structure that meets the criteria, and then apply the crosstalk effects onto the results. Okay, so there's some flexibility of specifying conditions for crosstalk. I'm going to cancel that, going to uncheck that, and this next box is what we call the power aware. This is IEEE standard in terms of IBIS model. So people like Micron will have power aware IBIS memory models for you to use. You don't have to use the power aware part, but you can, in our case, by just checking the box. That's it. And we will see if the IBIS file has the power aware capability, in which case we will use those. If it doesn't, then we will ignore. Okay, so this gives you a better, closer way, for accuracy. Like I said, it's like doing power integrity simulation without actually doing the real power integrity setup and simulation. Okay, now you can run into a case where if you don't enable this, things are passing, and if you do enable this, things are failing. That means your power delivery network is problematic, and that means you should do a separate power integrity simulation. Okay. And then this is just the last thing here where we want to run fast case, corner, typical, or slow. Now, as engineers, myself included, we were trained to do worst case analysis. So we automatically turn slow and automatically turn fast. We'll automatically turn everything on and we run. And the idea is let's generate everything, see what failed. And I got all this data, to look at. Don't do that. You are wasting time. You are running simulation over and over for all three cases. My recommendation is just to run it typical, okay, to see where things are. if you don't pass in typical, make it pass. And not just make it pass, make it centered. Make your timing margin, try to center everything in typical. And then once you're done with that, before you release the product, run one or two slow and weak. And hopefully by that time they will pass because you've done the typical and you centered everything already. And if they don't pass, then you deal with that later. Okay. We're still doing the same approach, but much lesser, effort. Okay, and then the ability to change thresholds value if you want. Right? I don't know why you want to do that, but you can. And then in addition to just checking normal timing, we will use JEDEC for you. We will apply JEDEC timing and values. So JEDEC comes in and say, okay, what are you? You are DDR3. Okay, then I will apply these limits and make sure your signal does not overshoot that much or undershoot or overshoot area or the symmetry of your differential signal, right? The skew has to be within a limit. You cannot have the positive signal switching at 0 and the negative signal switching at way sometime later. It has to be symmetric within some limits. These are JEDEC limits. So if you pass JEDEC limits, that means your memory, subsystem, controller, and chip and interface is JEDEC compliant, right? You still can get your system to work without passing JEDEC, but then you're not interoperable. You can't plug in somebody else who is, JEDEC compatible and expect it to work. But if you are JEDEC compliant, you can plug in people from, for JEDEC compliant, it will work. Okay, so those are the JEDEC parameters. And then these are just more stuff in here, which I won't go through necessarily. Now you may have some warnings from the model. Okay, so look through those, run the batch simulation, and let's just save it away. Give it my name, that's fine. So that saves all the setup, and then we're running. Okay, so now we're actually running. And I apologize, I'm running over time. I always do. Always just difficult subject. So we don't have that many people today, so feel free to inject questions if you like. We are running full timing analysis on all the signals of this real board, which is the BeagleBone board, and this is just DDR3. And we're just running right, and we're done. So just think about what just happened. We ran the whole analysis, all the writes, and we have this report, and it's showing us that, okay, these are the setup margin, whole time margin. I can just click in any one of these, and it will bring up the waveform. It will show me where that measurement was taken, right? So that's there. I can mark this, I can print this, blah, blah, blah. You sure control X, yes. You want to save? No. Okay. And that's the right case. This is the address lines. So we will see some margin is failing. There's some undershoot thing going on here. Undershoot 29 picoseconds for the cast signal, right? So what does that look like? Click on that. There's some undershoot going on here. And so exit, no, don't save, close. And then differential net. Do I meet JEDEC timing? Undershoot area, overshoot area. These are JEDEC parameters. These are not just normal parameters. VIX, the differential crossing, right? The symmetry between the plus and the minus. Some signal is very close. The limit was 150 and I'm 142 skewed. Okay. Clock to DQ skew. All of these you can click on and you get the result. Then the setup information, it tells you what do you use to set things up, ODT settings, IBIS model, so all of that stuff. So we had a failure here. We had a problem with the cast, right? So how do we debug that thing? Net we will say DDR star cast. For example, we search for that net. Here's that net, and it looks like this. Okay, it goes from the controller. Let me see. Let me assign this to be an output. Yep, it is an output, and it's driving through one layer in this way. Okay, which is not really optimum. Now, I don't know about you, but when you serpentine signal, you don't loop back like this, because when you loop back like this, there is coupling, self-coupling between the two nets, and it depends on the spacing between the two, right? You should always serpentine forward. You don't go back and forth like this. And then this one is changing. Now, I'm just saying this potential problem. I'm not saying it is problematic. And then you change layer and you hit to this device, right? So from here, what we can do is we can export this net to schematic, okay? And we will uncheck some of those stuff. And let's say what it looks like. You might be asking, hey, what do you mean? This board's been working. They've been selling this. 1,000, 100,000 of these things. How come you see problem? Well, it might be selling, it might not be optimized, and if something fail, so what? This is not used to control the missile, right? Or nuclear bombs, or who cares? This is not operating in Alaska or in the tropics. It's a development board. Use it as is. It works in temperature. Now, don't think that way for your product. You need to be more stringent. Okay, so here's the extracted schematic of that routed net. And what we can do is we can do a simulation, and let's just run a oscillator, and let's just run, I don't know, 400 megahertz, something like that. Say start simulation. Okay, and here's the zooming, and U5 is the driver controller, and here is U12, that's the memory chip. So this is what the signal looked like at the memory chip. And if you look at the threshold, it does cross through the high, it does cross through the low. It doesn't look very nice, okay? Will this work? Well, yeah. There is power implication, there's noise implication, there's EMI implication here, but it will work. Do you really want to ship your product like this? I don't know if you should do that. So what can you do? Okay. So what I can do, a lot of things I can do. I can change the trace, I can change V, I can change this, but what I will change is already the model settings. I go back to the buffer, I say select. Instead of using 5 milliamp buffer, I'm going to use, let's say, 8 milliamp, for example. Now, every driver is different. Every controller is different. So you can't just say 5, 7, 8. You choose different type. So I'm choosing a different type here. I said, okay. And let me just rerun the simulation. And let me just erase. Okay. And let's just zoom this. Now, I don't know about you, but this signal is better than the other one. The swing here is not as much. Okay, it's more square. It's cleaner than the other one by changing the milliamp. So, but there are implications here. The swing is a little bit higher, so maybe more power consumption. There's a little undershoot here. You may have to add in more things. But what I've just shown you is the whole flow. What we did was we took the whole board, okay, went to the wizard, specified the whole thing, the interface, ODTs, everything takes us, probably 5-10 minutes. I cheated because I load the setup file, but the real process takes about 5-10 minutes. We run the analysis, which takes a few minutes. We saw one error. We zoom into that. We look at the simulation standalone. We extract it out, and we were able to fix it, okay, by changing the driver. So it's really that quick. All right, so that's one demo. Any quick question on this? Okay, if not, I will go to the next one, which is, let's see, so that's post layout. What about pre-layout? Pre-layout, I will do DDR3. Okay, I'm not going to save anything. So as I mentioned before, the schematic that I'm going to be using is the same one was in the slide. So there's clock on the left, okay, there's address line, there's data mask, there's DQS in here, and there are 4 data lines. So DQ0, DQ1, 2, 3. Why 4? Because this one I have 2.5 inch. This one I have 3.25 inches, okay, and 2.75. So in one simulation, I can experiment different trace lengths. So what I do now, so as I run the same wizard, okay, it doesn't change. It's the same wizard that you run, okay, and I'll cheat again. I'll say import a setup file, okay, which basically said either 3, 1.5, 1600, U1 is controller, U2, blah blah blah, right? All this stuff, same thing. I'm not going to go through everything. So typical, blah blah. Just run through all this and say run. And let's just use me again. Yes. So it's the same interface, whether you have it post or run. No wonder it was hanging because I didn't click run. So this allows you to go through, what if I do this, what if I do that, you know, layers, trace length, termination, and we're done in pre-layout, and everything's passing. Hunky-dory, let's ship it. No, you need to look at it. Even though when it's passing, you can see DQ1 here has a setup of 119, but a hold time of 6 picoseconds. And then DQ2 has a setup of 0.2 and 131 hold time. So that's not good. We need to center this. And DQ3 is 80 and then 50 here, right? So let's say we want to improve the hold time on DQ1 and improve the setup time on DQ2. To improve the hold time, we need to add trace. To improve the setup time, we need to subtract trace. Okay, so we go back to here, and DQ1, we will need to add trace. Right now it's a transmission line. Right now it's 2.5. Let me just say 2.75 inches, right? And the Q2 right now is 3.25 inches. Let's just make it 3, for example. Okay. And let's just rerun the thing again. Just rerun this. Just say finish and run. And run. Again, I'm just showing you the easy thing, which is just a trace length, but you can also change, you know, via and add more transmission line and connectors, you know, whatever, changing the different layers, whatever you want. So we're done here again. And now DQ1, we added some trace length. So now it's more equalized, 77 picosecond setup, 54. DQ2, we reduce the trace length, which bring the setup time margin better. So you got 37, 98. So there you go. That's the process. Okay. So what if I have I am not using PAT. I'm using other type of format. I'll show you how to do that. So here we can use an Allegro board. Okay, so we'll use the Xilinx board. So what we do is we do a file translation. So first of all, we can bring in ODB++. So in case you have some board from somebody who's not PAT, who's not Allegro, who's whatever, but they can generate ODB++, we can bring in ODB++. Or in this case, we're going to run a translator, and it's going to be Cadence Allegro board file. Okay, so I'm going to select that, say OK, and we'll say translate and open, and we'll run through the translator, taking the BRD file and translate that into the hyperlink format. And it will take some time because this board is complicated. That's this board we're looking at here. Okay, so that's the board we're bringing in. That's a real board. So here's the case. Wow, I'm way over. So the first thing to do before you do anything, don't just go through to click the button and you know and simulate. You need to make sure your setup is correct. So check the stackup. The stackup of this board is actually looking weird. It does not have a solder mass definition. There's no solder mass. And number two, the thickness is weird. You see this 0.444 ounce for the signal layer, lots of these 0.4, and then you see 0.889 ounce, not 1 ounce, 0.889, and that's weird. Okay, and I think what happened here is people just use default number, you know, like 1.2 mil and 1.6 mil and 0.6 mil, and didn't think about using the board in simulation. So they don't prepare that because, oh, by the time when we fab the board, it will all be correct. But for now, when you simulate, just use this file. No, you need to use the same file that, you know, same parameters as what you'll be making. Okay, so make sure stackup's correct. Cancel this, and we can do the same thing. We can just say simulate SI, run the batch simulation. It's the same interface. I don't care how board comes in. So again, we'll import a setup file here, for example. But now we're running DDR4. Okay, now 1600. Next, here's the U1. Here's memory, right? 60 to 64, 5 chip because of ECC. And these are the models. And right cycle only. But notice, because of DDR4, we can do things like DBI, so data bus inversion. Okay, and then these are the signals, and there's some warning about models. Okay, next, here are the things that are specifically related to DDR4. So single VREF, one VREF for all the signals, or different VREF per bits per byte, you know, blah blah. So for the most part, it's exactly the same. Okay, and then you can just say run batch, save this away, run it. It will take about 1 hour to run the simulation on this DDR4, and you see the exactly same type of result that I just showed you with the smaller board. Okay, last demo I want to show you is the question becomes, oh, what if I don't have the model for the controller? That's problematic all the time, because you know sometimes vendor have problem giving you that file. So what is our solution for that? We have a generic controller that you can use. Okay, so to show you that, just to show you quickly, here is a mock-up design that we have, and I've shown you 2 real boards, so I have to show you a mock-up design. So here's a memory controller, here's that memory chip, DDR4, and we are now using scripts. Okay, so we have script editor. We can run Visual Basic scripts. Okay, and we can load in VBS file here. Okay, now don't be scared. View, can I zoom? Can I zoom? No, I can't. Okay, so I apologize for the small text, but this is Visual Basic script. Okay, you can write this, or you can use ours if you can customize things. Okay, so we provide these Visual Basic scripts, and then we can actually, select the net, for example. So here's A0. Here's the routing for that net. Kind of hard to see because of cyan. Okay, go through kind of things like that, and then you can just run the scripts. run this. Now, if you want to generate this for a selected net, you say 1, okay, and it generates all these scripts, DDR reference file and IBIS file for you. Or if you want to use a reference designator, you can do that. Okay, so I want to use number 2, and what designator you want? I want U 100, for example. Okay, there, done. And after that, you just run the wizard again, right? So run the batch simulation, and we'll import it one more time. Demo board, open. And so this is saying run DDR4, 2400. Here's the controller. Here are the memory chip, right? 4 of them, 4 or 5 of them. Generic models, read-write cycle, blah, 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 all that stuff. Same interface. But what I want to show you here is in the ODT, we're choosing IO 40, and the other one is, so everything's 40 ohm, right? When you run this and get the results, this will be done very quickly here. So here is the result. We will see that it's failing. It's failing on the right. A lot of failures on the right. Okay, there's some failure on the reads. Okay, so what do we do now? Pretty easy. You will go through and change your ODT, and when you do that, everything will be passing. Okay, so let me show you that a little bit here. Where is it? Oh, I closed it. Done. Okay. EMO hyperlinks 19. This data pass results. Okay. So in this case, we use a generic model and we change the ODT settings, and now it's working. Okay. So here is the setting. So we're using IO 34 ohm, and the other guy we use 48, and 50. So, but through the generic model, I am able to figure out, if my routing is problematic or not. And based on this, and while I'm waiting for the real IBIS model to arrive, I can actually do things. And right now we have this capability for DDR4 with the generic, and I'm sure they'll have, for DDR3 and maybe something else. But this relieves you from needing to have the real IBIS model. So in summary of all the demos, I showed you how to do post layout simulation for DDR3. I showed you how to do pre-layout simulation for DDR3. I showed you how to set up on a Xilinx ultra scale board for DDR4 post layout. And the last demo was I showed you how to model DDR simulation using generic IBIS model, but only for DDR4. Okay, so this should cover a lot of cases out there. Okay, questions? I'm done. Apologize for exceeding time. We're still here? Okay, so if there is no question, I will stop the recording.